Okay, so I'm going to talk a little bit about capacitors so that you're ready for the lab where we're going to measure the charge in a capacitor and relate it to the voltage and the capacitance. So remember, a capacitor is two plates separated by some distance, and it has a value of capacitance C, and we'll talk about how that value can be calculated in class. But the critical relationship is that the charge on the capacitor, which you can think of as the amount of positive charge, and equivalently the amount of negative charge. The charge is considered to be the total amount of positive charge, if you like, on the capacitor, or the total amount of negative charge. The net charge on the capacitor is always zero, but the amount of charge that we're going to use in calculations is going to be equal to the amount of either the positive or the negative charge. Alright, so the relationship that you'll have, that I mentioned in class briefly, is that the charge on the capacitor is equal to the capacitance of the capacitor times the voltage drop across the capacitor, where the voltage drop is simply the voltage measured across the two terminals, one here and one there. So that voltage you could use with you could measure it with a multimeter, multiply that times the capacitance, and you get the charge. And so in lab, you're going to actually measure the charge on the capacitor by measuring how much a needle swings of a device called a galvanometer. Okay, so what I want to show you today, though, is what happens if you put to the value of the capacitance. And by the way, the capacitance is kind of like a cup that stores charge. Alright, if you think of it like a cup, that's one way to imagine this. And the units are farads. Now typically capacitors you're going to see are going to have sizes of microfarads or even smaller. A farad is a lot of capacitance. It's a lot of capacity, ability to store charge. Okay, so I'm going to go to the next slide here and talk to you about just what happens if I were to put capacitors in series. Now, a series circuit of capacitors means that you have two capacitors in a row. So if there were a current that was able to flow through this, which it can't for very long, as you'll find out later, it would flow through both of them. That is considered to be a series, or a series combination of capacitors. A parallel combination of capacitors looks like this. And what I want to show you is that when you combine capacitors in series, you're going to get a certain new capacitance or an equivalent capacitance, and when you combine them in parallel, you'll get a different equivalent capacitance. I'll start with the case of the parallel. So if I were to put two capacitors in parallel, that means there's a certain amount of plus charge on this plate of this capacitor, and there are two different capacitances, C1 and C2. There's a certain amount of plus charge on this capacitor, and minus on this one, and minus on that one. Okay, so when they're in parallel, the voltage across this set of capacitors is V. It's whatever battery voltage you put on it there. And then the relationship, of course, that we're going to turn to is that Q is equal to CV. So if we want to find out what the equivalent capacitance is, call that C equivalent. Whoops. C equivalent is equal to, therefore, Q divided by V. So whatever charge this battery here sees stored on whatever series of capacitors is here is related to the equivalent capacitance. So I could replace these two capacitors then with a single capacitor, and that's what I want to find the value of. Very similar to what we were doing with resistors. Alright, so what's going to happen then if I have this voltage here on this capacitor and this voltage here on this one? Well, what's going to happen is that because these capacitors are in parallel with this source here, each capacitor is going to have the voltage V across it. I inadvertently drew it, but that's correct. Each capacitor is going to have that voltage V. So the charge on each capacitor is going to be different. The charge on each capacitor, the charge on capacitor C2, I'll call that Q2, that's going to be equal to C2 times V. Similarly, Q1, the charge on this capacitor right here, is going to be equal to C1 times V. So the total charge that this voltage sees then, that this voltage here sees, is going to be equal to, I'll call it Q total. It's equal to Q1 plus Q2. It's going to see both of those charges together. Alright, so now let me substitute this in this equation here and find out what the equivalent capacitance is for two capacitors in parallel. The equivalent capacitance we're going to see is equal to, Q is equal to CV. So C is equal to Q total. Call it C equivalent. That's the total capacitance in the circuit, is Q total over V. So the voltage V is just V, but Q total is equal to C1. Whoops. C1 times V plus C2 times V divided by V. And I might have skipped a step here, but Q total, this here is Q1 plus Q2. And that's what got me to this step here. Q1 is C1 times V, Q2 is C2 times V. So if I look at this, I can factor out the V here. So the V is going to cancel on the top and on the bottom. So I would get that for parallel capacitor circuits, the equivalent capacitance is simply the sum of the two capacitances. Something we'll use when calculating it. Alright? Now what about if the capacitors are in series? How does that work? When capacitors are in series, you can look at it similarly. So in other words, if I have a battery here, a power supply, with a voltage V, and I have a capacitor here C1 and another capacitor here C2, each one is going to have a different voltage because the sum of the voltage across this one and the sum of the voltage across that one, the sum of the two voltages is going to be equal to the source voltage. So what I can say is, I can say that V total, or the source voltage, is equal to V1, it's the voltage across capacitor C1, plus V2, which is the voltage across capacitor C2. So that's one relationship I have. The other relationship I have is, let me look at what's going on with the charges on this capacitor. On this side here, I'm going to have plus charges from the battery. Those are going to cause minus charges on this side to collect. And, of course, the net sum of the two of these is going to be 0. But when the minus charges move over to here, to this side, like that, that means they separated from the plus charges over here. Because the net charge in this center island here that I'll circle in blue, the net charge here is 0. These minuses on the left side have to cancel with the positive charges on the right side. Alright, so keep that in mind. And then on this right side of the rightmost capacitor, whoops, I drew an extra. There we go. There's going to be the same amount of minus charges here as there is here, which is going to be the same as the amount of plus charges here and here. Okay, so what we can say then is that that on capacitor C1 I have Q1 here, or Q, and I have the same charge here. By necessity, whatever charge I have on the first capacitor has to be the same as the one on the second when they're in series, no matter what the value of the capacitor is. So this here becomes equal to, so V1 I can say is Q over C1 plus Q over C2, where the Q on each capacitor is going to be the same thing as if there were just a single capacitor here. And I replaced this circuit over here with just a single capacitor. It's going to have voltage here, V, and a charge here, Q, where this Q is going to be the same size as these Q's. Alright, so I'm going to go to the next slide. Okay, and on this slide, what I'm going to say is and I'll put in my result from the last slide, where V is equal to so then I can substitute it in. The Q's are all going to cancel, and I get 1 over C1 plus 1 over C2. So this is the equation for the series capacitor, or any number of capacitors in series. You're going to take the inverse of each capacitance, add those together, and divide that sum by 1. So the series capacitors look like parallel resistors in terms of determining the equivalent capacitance. So I'll just write that. So to summarize, so for capacitors in series, we have that C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus however many you have. And for parallel, you could say that the equivalent capacitance is equal to just simply the sum of however many capacitors are in parallel. Okay, hopefully this will help you.